Welcome back to our session. We're still working with redox reaction. Now we have arrived at a point where we appreciate that there is a reactivity series that we can use, as a way of comparing, the relative strength of different substances in terms of their reducing ability or their willingness to actually lose electrons in the transfer process, which happens in a, typical redox reaction. Now let's look at another example, okay? But before we do that, the table of standard reduction potential, what exactly does it do? Instead of us using the displacement reaction, because in a displacement, we are saying magnesium displaces zinc. So in other words, zinc is a stronger reducing agent compared to magnesium. So instead of using these displacement reactions to actually establish the order table of reducing agent and oxidizing agent, the chemists actually can measure the extent of reduction using the electrochemical cells. So these electrochemical cells is a way of actually trying to get to a point where you are able to compare different substances in terms of their reducing ability. And also think of it, we can talk of these substances in this standard reduction potential table in terms of their reducing ability or in terms of their oxidizing ability. Because we are saying that, by all means, a stronger reducing agent, if it's compared to another substance, it is actually a weaker oxidizing agent. And the opposite is true for those two substances that are involved. So the displacement reaction actually gave us a way of trying to measure or compare, the relative strength of different substances in terms of their reducing ability. Right. So this is the table of the standard reduction potentials, okay, of different substances. So if you look at the arrow on the right hand side, it says to us increasing reducing ability. So what are we saying? We are saying that lithium is a stronger reducing agent compared to, say, for argument's sake, if we compare lithium and potassium compared to potassium. So we are saying that lithium can displace potassium in that order, right? Okay. So this is the different substances now listed in the sequence or in the series in terms of their reducing or oxidizing ability, right? So hence we are saying that if you look at it from top to bottom, it's in terms of oxidizing ability. But if you look at it in terms of bottom to the top, it's in terms of reducing strength, okay, or reducing ability. So we are saying that the reducing ability actually increases as you go up that series, and the oxidizing strength of the substance actually increases as you go down the series, right? Okay, now we want to make use of this table of the standard reduction potentials to actually write balanced chemical equations for the reaction between aluminium and iron 3 oxide, right? So we will make use of the table, okay? Now, this is the table. The substances that we are interested in is actually iron 3, okay? And so this is our iron 3, as well as our aluminium, right? There is our aluminium, okay? Now, if you look at this table from top to bottom, it says, as you move up that table, the strength of reducing agent increases. We are saying that the topmost substance actually shows greater readiness or willingness to actually lose electrons. Why lose electrons? Because we're talking about its reducing ability. And a reducing agent actually shows greater readiness to donate or lose in the process undergoing oxidation, because that's what exactly a reducing agent actually does. It undergoes the loss of electrons, right? So if we are to do that, we are saying that aluminium is a stronger reducing agent than iron. So we can represent the top equation, because that says the equation can be interpreted left to right or right to left. So in this case, it's going to be aluminium undergoing oxidation. Now it goes in one way because the comparative strength of the two. Then we get aluminium ions plus 3 electrons, right? While the one below is going to be iron 3 plus 3 electrons to give us aluminium ions. So the first half reaction would refer to it as we have seen in the previous example, as the oxidation half reaction, while the one below is the reduction half reaction. But of particular interest to us, again, is the role of each of these. So aluminium is a stronger reducing agent, okay? All right. While the iron 3 is an oxidizing agent. So these are the two half reactions that are undergone in this reaction between iron and aluminium, right? So if we are to do that, we can also say, okay, these are the half reactions, so but we want to write a balanced reaction for both of them. So the number of electrons lost by each aluminium is 3. And then for every Fe3 plus ion, there are 3 electrons gained. So what is lost equals to what is gained. So we can simply say, in terms of the net ionic equation, we'll have aluminium, okay, plus ion 3, okay. Okay, we made a mistake here. I think we need to have, just to correct that, we can't have aluminium on the second one. Okay, take note of that, you know, because it's just an oversight. So we will have iron instead, okay? So if this is going to give us what? Aluminium ions, okay, plus iron. So this is the balanced equation of reaction. Okay. We can also look at different examples by making reference to the standard reduction potential tables. But if we are to keep track in terms of balancing, let's also pay attention to the electrons involved in each of those half reactions. So this reaction involves hydrogen sulfide and potassium dichromate, right? Okay. So if we are to look at hydrogen sulfide, we have to identify the reaction involving hydrogen sulfide. In this case, this is the reaction that we're talking about. So this table will actually be given, you know, even in an exam. Yours is just to understand how to use it and which equation is relevant depending on the question that is given. So you don't necessarily have to memorize all these equations. It's quite a lot of it. So understanding is very, very key, right? So this is the first equation. Now we are going to compare it because the table is it's quite long, and then there is the second part of it that involves the dichromate. There is the half equation concerned, okay? So already we are seeing that the dichromate reaction is bottommost. So it means this dichromate one actually has to do with the reduction, because it is saying as you go down the table, the strength of oxidizing agent increases. While if we can go back, as you go up, the strength of reducing agent will actually increase, all right? So at the end, it gives us that. So we want to understand that, okay, the hydrogen sulfide is actually our reducing agent as per the table. So if we were to rewrite this equation, we'll have our hydrogen sulfide, okay? Take note of the formula, which is a gas, okay? Undergoing oxidation to give us sulfur atoms, okay? The hydrogen ions in solution, okay, plus 2 electrons, right? And then the dichromate one, but take note again, the symbol now is left to right. The dichromate one will be Cr2O7, 2 minus, plus 14H plus. So this 14H plus tells us that this half reaction of reduction occurs in an acidic medium, plus C electrons, 6 electrons. So the 6 electrons are actually gained, which gives us the reduction half reaction to give 2 Cr3 plus, okay, which goes into solution, plus 7 water molecules. Right. Now, these are the two half reactions. So that's our oxidation and that's our reduction. So this is our oxidation half reaction, and the below one for the dichromate is our reduction. So for us to balance the number of electrons, the thinking is whatever is lost must be equal to what is gained, which is also equal to what is transferred between the reducing agent as well as the oxidizing agent. So if you check here, I think even from a simultaneous equation, to actually balance the electrons, we can multiply this by 3, and this one by 1. So as a result, we'll have the equal number of electrons becoming 6 lost, 6 gained, right? So if we do that, obviously the electrons will cancel themselves out. Now, if we multiply this by 3, then we'll have 3 hydrogen sulfide, okay, plus, okay, the dichromate, Cr2O7, 2 minus, okay, plus 14 hydrogen ions, okay, to give us 3 sulfur, okay, plus, if we multiply that by 3, it will give us 6 H plus, right? Plus, if we multiply the chromium ion 3 plus, it will give us by 1, it will give us 2 Cr2 plus, okay, plus 7 H2O. All right, okay, but you'd realize that on the left, we've got 14 hydrogens and we've got 6 on the right. So you can immediately say, okay, actually the hydrogen ions will remain on the left because we've got 14. So if we subtract that, we actually get 8. So we can actually get rid of those ones on the left-hand side and actually say, okay, we are left with 8. So this becomes our balanced equation of reaction, okay? So, okay, that's our balanced equation of reaction. So this is how we actually use our standard reduction potential tables. So in summary, what are we saying? Redox reactions actually involve the transfer of electrons. So in the transfer, there's the loss and the gain. These happen simultaneously or at the same time. And also, in every redox reaction, there is an oxidizing agent, the substance that loses, and the reducing agent, the substance that actually gains. So, and overall, the table of the standard reduction potential is an order of list of these half reactions in terms of oxidizing agent and reducing agent. I think beyond these few examples that we have used, I think it's very important to emphasize that a lot of practice will actually go a long way in terms of getting into grips and understanding the concept behind, of what happens in a typical redox reaction. With that said, that's the time we had for today. Goodbye for now.